There's one last topic I'd like to cover in this unit, and again, it's related to the analysis of graphs and paths and using variants of depth first and breadth first search to answer questions about the graph. Here's a little graph that I drew, and one thing that we might notice is that everybody's connected to everybody else, but there is this sort of weak edge. This is the weakest link. Hello. If this edge were to be removed from the graph, like so, the number of components in the graph has just gone up by 1. Now, that was the only edge in this graph that has that property. There's other edges that if we take them out, things are still connected. So in some social networks, it's useful to know, are there any edges in this graph? Are there any pairs of people in the graph that are connected that if they were to, say, stop being friends, there would be disconnection in the network as a whole? So let's put this edge back in and label the edges, label the nodes of the graph so we can talk about them. And we're going to carry out an algorithm that goes back to 1974 by Robert Tarjan. Tarjan is responsible for some of the most amazing graph algorithms, a lot of which are based on the ideas of building trees, spanning trees, using depth first and breadth first search. Back in college, my friend Chris M. and I used to refer to him as Tarjan, Lord of the Trees. So the basic idea of this algorithm is that we pick any node in the graph, let's say B, and we start to build a tree starting from B. And here's how we do it. Starting from B, we look at all the neighbors of B, which in this case are A and C, and we haven't built any of them into the graph yet, so we can add them into the graph. And now we do essentially a search, just as we were doing before. We have visited A and C. So from A, we look at the neighbors of A, and the neighbors of A are B and C. Now, the BA edge is already in there, but the BC edge is not. And so we're going to add a special kind of edge because this is an edge between two nodes that are already existing. We'll call this a non-tree edge, because what we're going to do is we're going to take this entire graph and express it essentially as a tree, but some of the edges aren't going to be part of the tree. We're going to have to add them in separately. All right, so that takes care of all the neighbors of B. The neighbors of C, we have B, which is the edge is already in there, and we also have an edge to E, which we haven't seen yet. So we add that edge in, and then we proceed from E. Now E has 3 edges, back to C, which we already have, and also to D and G. And those are new nodes, so we build them in with tree edges. And we continue our search. Now let's say from D. D has two neighbors, E and F. E is already in there, but we can add in F as a tree edge. We look back at G. G has neighbors F and E. The E one is in there. The F one is not, so we add that non-tree edge in there because F is already in the diagram, but that edge was not. And then from F, there's connections to D and G, and those are already in the graph. So basically what we've done now is we rewrote the original graph as a rooted tree. So starting with some node and then proceeding downward. And then any edges that don't really fit that pattern we put in as little red dotted lines. So we've rewritten the graph as a tree. And the next thing we need to do is post-order the nodes. Now, post-ordering is something you can do to any tree structure, and it basically involves assigning a number, a sequential number, to each of the nodes in the tree. And post-order means that what we do is to assign a number to a node, we first make sure that all the children on its left are numbered, all the children on its right are numbered, children and descendants, direct children and also their children's children. And then the node itself gets a number after that. So B's number is going to come from first numbering A. Well, A has, and then everything below C, and then we can number B itself. A's number comes from numbering its children, which it doesn't have any. So it can get whatever the next number is, which in this case is 1. All right. So back to B, we have to label all the children on its left, all the children on its right. Well, we haven't done that yet. So let's do a numbering starting from C. Well, C, before it gets a number, it has to have all its children numbered. And we can see that they don't have numbers yet, so we have to proceed down the tree. E needs a number. Well, E can't get its number until its children have been numbered, but they haven't been numbered yet, so let's number those. D should get a number, but first its children have to get a number. This is a, children first sort of scheme. D's children has one child, and that's F. For F to get a number, its children, it doesn't have any children yet. All right, so F can get the next available number. In this case, it's 2. So now that that's finished, D can get a number because all its children are numbered. So D gets the next available number. That's 3. E still can't be numbered because its children haven't been all numbered yet. We have to go to G first. G has no children, so it can get the next available number. Now E can get a number. Post order in this case is post meaning after. After all the kids, the node itself can get numbered. There's also pre-order and in order, but we're just looking at post order for this algorithm. All right, now C, all its children have been numbered, so now C can get its number. B, all its children have been numbered, so now B can get its number. So we've now post-ordered all the nodes in the graph. So just to make sure that you're understanding that process, here's a different tree. This time the branching factor is a little bit different in some places. And I want you to post-order this tree and then type in this box the number assigned to node P once you've done that.